Have you ever peeked at a kid's math homework and just thought, what is this? This looks nothing like how I learned it. Well, if you have, you are definitely not alone. Today, we're going to dive into why math class has changed so much, moving from just memorizing rules to a whole different way of thinking. And it's not just parents who are scratching their heads. This question from a Reddit user really gets to the heart of a frustration that, let's be honest, a lot of us have felt. It's that nagging feeling that we're just, repeating formulas without ever really getting it. This has been the big puzzle in math education for ages. Is there a better way to learn this stuff than just memorizing a bunch of rules? Well, let's dig in and find out. Okay, so to really get this, let's start by looking back at the kind of math most of us probably remember and talk about some of its limits. That classic approach, it's all built on something called rote memorization. And a user on Reddit put it perfectly. It's when you can spit out the fact that 3 times 5 equals 15, but you have absolutely no clue why that means 15 divided by 5 has to be 3. You know the what, but you're completely missing the why. And that's the key difference right there. Rote knowledge versus conceptual understanding. Rote knowledge is all about just following a recipe, a set of steps you've memorized. But conceptual understanding, that's when you can actually explain why the recipe works in the first place. And get this, it's not just a problem for little kids. Research shows this stuff follows students all the way to college. You have university students who are still struggling with basic algebra because they only ever memorized the steps in high school without ever understanding the concepts behind them. So what's the fix? Well, the big shift starts with a completely different approach, and it's called active learning. What's so cool about active learning is how it works. It's not just about getting kids to think harder. It's about engaging them on 3 different levels all at once. Intellectually, of course, but also socially and even physically. So what does that even look like in a real classroom? Well, it could be anything from hands-on stuff like folding paper to understand fractions, to these collaborative sessions called gallery walks, or even taking the classroom outside for math trails. I mean, just look at this. You can see the focus is on actually doing things. On one side, you have a student really zeroed in on a paper folding task, a super tangible way to get a feel for geometry. The main idea, whether you're working alone or in a group, is always the same. You learn by doing and by talking about it. Let's break down that gallery walk thing because it's pretty neat. It's a structured 6-step process. Groups solve a problem, put their solution up on a poster, and then, here's the cool part, they walk around and analyze and comment on what other groups did. It completely changes a boring old worksheet problem into this lively social event where you're learning from everyone. Okay, let's talk about the other huge piece of the modern classroom, technology. But its real power isn't what you might think. To make sense of technology's role, a lot of educators use this simple model called the RAT framework. Technology can just replace an old tool, like a worksheet becomes a PDF. No big deal. It can amplify a task, making it faster or more efficient. Or, and this is the real goal, it can transform learning into something that just wasn't possible before. And that transformation, that's where the magic is. We're talking about moving away from one-size-fits-all lessons to something that's customized for each student. It means going from a flat, static picture in a book to a dynamic, interactive model you can play with. And maybe most importantly, it's about shifting the focus from the teacher lecturing at the front of the room to the students really exploring on their own. But, with all these new ideas flying around, it's pretty easy to get carried away. So let's hit pause for a second and look at what the actual evidence says about some popular myths in teaching. All right, here's a big one you hear all the time. The myth is that a student has to completely understand the big idea, the concept, before they can learn the steps to actually solve the problem. But it turns out the research says that's just not quite right. The truth is, it's a two-way street. Learning the steps can actually help you understand the concept, and understanding the concept makes it easier to remember the steps. They help each other out. They build on each other. Okay, here's another super popular idea, productive struggle. This is the belief that the best way for students to learn is to just let them wrestle with a really hard problem all by themselves. But what do we really mean by struggle? I love this quote from a couple of experts, Heber and Grouse. They make it clear that true struggle is about putting in the effort to make sense of something. It's not about needless frustration or being faced with a challenge that's just impossible. There's a really important difference. So here's the bottom line from the research. While effort is absolutely crucial, For students who are brand new to a topic, just letting them loose with unguided discovery often leads straight to that needless frustration. For a beginner, clear, direct instruction from a teacher is often way more effective. So, if we pull all of this together, what does it even mean to be good at math anymore? I absolutely love this analogy from Reddit because it just nails the balance we've been talking about. Math is like basketball. You 100% need to do the drills, that's your basic skills. But to really get good, you have to actually get in the game and play, and that's using your understanding to solve real problems.
So what can all of us take away from this? A few things. First, always ask why a formula works, not just that it works. Second, try to visualize the problem. Seriously, draw a picture. It helps. And third, a fantastic way to test if you really get something is to try and explain it to someone else. If you can't, you probably don't understand it as deeply as you think you do.
And that kind of brings us to the big final question. What if we've been measuring the wrong thing this whole time? What if being good at math has nothing to do with how fast you can find an answer, and everything to do with how curious you are to understand the question in the first place? Something to think about. Thanks for tuning in. Let's be honest. You see that tiny little number floating next to a big one, or that weird checkmark symbol? And for a lot of us, our brain just, well, it just short circuits. It's a feeling so many of us have, even years after we've left a math class. But why? What is it about these symbols? So let's really dig in. Why do these specific things trip us up so consistently? It's not random. And what's really fascinating is that the answer tells us something pretty fundamental about how all of our brains are wired to learn. Okay, take a look at this. This right here is probably one of the most common ways our intuition leads us astray. Our brain sees a repeated number, and it immediately jumps to a pattern it knows really well, adding things together. But an exponent isn't about addition at all. It's a shorthand for multiplying something by itself over and over again. It's a really subtle leap in logic, but it's the very first crack where understanding can start to crumble. So first, let's just frame the problem. We're talking about what are arguably some of the most confusing symbols in all of mathematics. And this is so important to get. If this stuff trips you up, it does not mean you're bad at math. It's all about pattern recognition. See, our brains are literally built to find shortcuts. But when you try to apply those shortcuts to abstract rules you haven't fully grasped yet, you can end up going down the completely wrong path. It's a feature, not a bug, of how we learn. All right, so to untangle this whole mess, we have to go back to square one. Let's get absolutely crystal clear on what these symbols are actually saying. At its very heart, an exponent is just a lazy way to write repeated multiplication. I mean, instead of writing out 3 times 3 times 3 times 3, you just write 3 to the power of 4. It's a shortcut. You could almost call it a piece of mathematical slang. That's really all it is. So the formal definition you see here says it's the power to which a base is raised. In our example, 3 is the base, 4 is the exponent. Simple as that. And then you've got the radical, which is basically the flip side of an exponent. That checkmark symbol, that's the radical. The number tucked inside is the radicand. And see that tiny number in the corner? That's the index, and it's the boss. It tells us which root we're supposed to find. Square root, cube root, whatever it is. Okay, definitions are locked in. Now let's get into the mental traps people fall into. And trust me, this is where it gets really interesting. First up, the even root trap. Your brain looks at the square root of -10 to the 4th power, and it says, oh, easy. The root and the power cancel out, so the answer is -10. Makes perfect sense, right? But here's the trap. With an even root, like a square root, the final answer can't be negative. You have to take the absolute value, which makes it +10. This one little rule trips up just about everyone. But now watch this. This is what makes it so confusing. If we switch to an odd root, like the 5th root of -10 to the 5th, the rules completely change. A negative number can go in and a negative number can come out. That absolute value rule, gone. The answer is -10. Having two totally different rules for even and odd roots is a classic source of confusion. And then you get to fractional exponents. This is where the wires can really get crossed. It's so easy to mix up what the top and bottom numbers do. People often think the denominator, the 2 in this case, is the power. But it's not. It's the index of the root. And the negative sign? That just means flip the whole thing into a fraction. So a to the -7/2 actually becomes 1 over the square root of a to the 7th. And look, this isn't just some small, nagging issue. In her research on this very topic, Feiruz Farah Sarkis found that this specific confusion, The link between radicals and exponents was the #1 source of mistakes, the, quote, highest frequency. So if you've ever felt totally lost here, you are in very, very good company. So what's the solution? How do we fix this? It's not about just trying harder. It's about fundamentally changing how we learn this stuff in the first place, shifting from just memorizing rules to actually building and understanding. Okay, let's make this real. Forget the abstract symbols for a second and just picture this, a wildfire. At 10 in the morning, it's burning 4 acres. And every single hour, the size of that fire doubles. How would you even begin to model that kind of growth? Well, let's just follow the logic. At the start, hour 0, it's 4 acres. After 1 hour, it's 4 times 2. After 2 hours, it's 4 times 2 times 2, which is, wait a second, just 4 times 2 squared? And right there, just like that, the exponent isn't some arbitrary rule from a textbook. It's a tool. It's a way to describe explosive real-world growth. That little t in the equation becomes a way to see into the future of that fire. And this is a perfect illustration of a huge shift in how math is taught today. The goal isn't to just hand students a list of rules and say, memorize these. It's about building those rules from the ground up, using real examples. You start with a pattern, and you let the learner discover the rule for themselves. A great example of this is something like a card sorting activity. You give students a bunch of cards with different expressions, like 2 to the 6th, or 4 to the 3rd, or 8 squared, and you just ask them to group the ones that are equal. By physically moving them around and talking about why they match, they start to build those connections in their own head. It's so much more powerful than just reading it in a book. So the whole point is that real understanding is built on strategies like these. It's about taking the math off the page and plugging it into the real world, like we did with the wildfire. It's about playing detective with patterns to discover the rules for yourself. And maybe most important of all, it's about asking that one simple question. Does this answer actually make sense? That's the leap from just calculating to truly reasoning. And that brings us to the core idea, the single most important takeaway from all of this. Because, getting the right answer is one thing, but true mastery, the kind of knowledge that actually sticks with you for life, is about understanding why it's the right answer. It's the difference between just following a recipe and actually knowing how to cook. So let's just bring it all home. Those tricky rules for even and odd roots, they're not random. They're different for a very logical reason. The laws of exponents aren't magic. They're just a direct extension of basic multiplication. Grounding these abstract ideas in real-world models makes them finally click. And the biggest takeaway of all, reasoning your way to an answer is always, always more powerful than just memorizing a rule. This shift from just memorizing to truly reasoning, that's what makes these intimidating symbols finally click into place. It transforms math from this dry list of rules into a language for describing the world, which leaves us with a bigger question to chew on. If this kind of thinking is the key to unlocking math, what else can it unlock? Hey everyone, and welcome. Today we're going to talk about something so many of us can relate to, the math classroom. We're going to look at how we can transform it from a place where you just memorize formulas to a place where cool concepts like probability actually make sense and, well, stick. Let's get into it. I want you to think back for a second, back to your school days. Remember sitting in math class, watching the teacher scribble on the board and just thinking, when am I ever going to use this? Yeah, we've all been there. But what if the problem wasn't the math itself? What if it was how it was being taught? This quote from an educator named Jessica Fauser just hits the nail on the head. In so many classrooms, learning becomes this cycle of just copying what the teacher does and then spinning it back out for homework. Students aren't really learning how to think for themselves or even how to use the textbook sitting right in front of them. So here's our roadmap. First, we're going to dig into the problem. Then we'll explore 3 key ways to fix it: building a solid foundation, making learning playful, and making sure we're teaching every kind of learner. And finally, the big one, we'll look at the proof. Does all this actually work? All right, let's start by really unpacking what's going wrong, because this isn't just about kids getting bored. It's about a bigger issue, a failure to build the skills they actually need, like resourcefulness and how to solve real problems. Fausto noticed something that's kind of huge in her classroom. When students got stuck, what was their first move? It wasn't to look back at their notes or check the book. Nope. It was to immediately put their hand up and ask for help. And that creates this dependency, right? It stops them from becoming confident, independent problem solvers. So, how do we start to fix this? Well, the first step is to actually teach students how to learn. We've got to give them the tools to organize information for themselves so they can go from being passive listeners to being active drivers of their own education. And the solution starts with something pretty simple, but honestly, it's brilliant: the math journal. Now, this is not just a regular notebook for scribbling down problems. It's a structured system that helps students really process and own new ideas, turning their notes into a personalized textbook they'll actually want to use. The real power of this journal is its structure. For every single new concept, let's say permutation or probability, students break it down into 5 simple parts. What's the definition? What's the equation? Can you draw a picture of it? Give me an example. And here's the most important one: what are its real-world uses? This simple framework forces them to engage with the material on a way deeper level. Okay, so once students have this framework for learning, we can start building on it. This is where we get to ditch the boring lectures and bring in hands-on activities that make these abstract ideas feel real. And dare I say it, actually fun? And this is where you can really see the transformation happen. So instead of a teacher lecturing at the board, picture students literally throwing a ball at a target to figure out probability. Instead of just copying down formulas, they're playing a game show to see how new information changes the odds. It's a total shift from being passive to being active. And the possibilities are just fantastic. You've got things like a target toss or a percentage race that turns a boring review sheet into a fun competition. There's even a project where students go research carnival games to figure out the actual odds of winning that giant stuffed animal. It's all about connecting math to things they can see, touch, and get excited about.
But, a great classroom isn't just about having cool activities. It's about making sure those activities work for everybody. And that brings us to something absolutely critical: differentiated instruction.
The main idea here is super simple, but so powerful. One size does not fit all. Truly effective teaching means you're always adapting, always modifying your lessons to meet the unique needs of every single student in that room, right where they are. So let's make this real. For a student with ADD, a long lecture can be a real struggle, right? So what's the adaptation? It's simple. You break up the lesson. You have them use physical objects or even act out a probability problem. It's a small change that makes the learning physical, turning a moment where they might zone out into a moment where they're totally engaged. It's the same idea for a student with a learning disability. A huge page of homework can feel impossible. The fix? A shorter assignment that still hits all the key ideas. Or maybe note-taking is tough for them. Okay, then you give them an outline beforehand. These little adjustments can make an absolutely massive difference. And this goes for your advanced learners too. For that gifted student who blows through the assignment in 10 minutes, you don't just give them more of the same boring problems. No way. You challenge them to think bigger. Ask them to figure out why the formulas work, or have them create their own tricky probability problems for the class. That's how you keep them hooked. So we have all these amazing ideas, right? Structured journals, active games, teaching that's inclusive. It all sounds great. But here's the million-dollar question. Is there any actual proof that this stuff works? Let's check out the data. And the answer is a huge yes. A massive review by PBS looked at the impact of their educational resources, things like videos, games, and lesson plans that use all these active learning ideas. The result? It's pretty staggering. In 90% of the studies they looked at, these modern teaching tools had a significant positive impact on how much students learned. And we're not talking about a tiny little bump. When it came to actual scores, one study found that students who used these kinds of digital resources on a regular basis, they outperformed the national average by 10 percentage points. 10 points. That is a huge leap. But it's not just about test scores, is it? It's also about the experience. Look at what the students themselves had to say. 54% said class was more interesting, 50% felt like they learned more, and almost half said the class was more challenging, in a good way. This approach doesn't just improve scores, it improves school itself. So the takeaway here is just crystal clear. When we finally move past the old school lecture and start using strategies that are active, engaging, and designed for every student, the results really do speak for themselves. You get better scores, and you get a better classroom. And that brings us to our final thought. The evidence is all there. The strategies are clear, We know how to build a math class where students don't just get by, but actually thrive. So the real question isn't whether it's possible. It's what's going to take to make this the new normal for every student.
All right, we're going to talk about high school geometry. Now, if that word just gave you flashbacks to, dusty textbooks and endless proofs about triangles, you're going to want to stick around. We are about to tear down what modern geometry class is really all about. So let's just get right into it. Is geometry just some abstract logic puzzle? Another box you have to check before you can move on to the more interesting math? For a long time, yeah, that was pretty much the vibe. But the way it's taught today, it's completely different, and it's aiming for something so much bigger.
Because, let's be real, geometry isn't just stuck in a classroom, it is everywhere. And the stuff you see here, these aren't just made-up examples. What's wild is that they're pulled directly from the national standards. We're talking about the actual skills you need to render video games, to design clothes, or even build a house. This is geometry as a practical, hands-on tool for messing with the world around us.
Okay, so how did this big shift even happen? Well, it wasn't an accident. There's a very deliberate plan, a blueprint behind this whole new approach. So let's pull back the curtain and look at the big ideas that are completely reshaping the subject. And that blueprint is the Common Core State Standards for Math. Think of this document as the master plan. It doesn't just lay out what kids should learn, but it sets up the whole philosophy for how to teach it. It's the why that drives all the what. And this right here, this is the absolute heart of the new approach. Instead of just staring at static shapes on a page, modern geometry starts with movement. The huge idea is that we can understand if two shapes are identical, or congruent, by seeing if we can slide, turn, or flip one to land perfectly on top of the other. These moves, the slides, turns, and flips, are called rigid motions. So the crucial thing to see here is that this new way of thinking weaves a bunch of big ideas together. First, like we just saw, it's all about understanding shapes through transformations. Second, it brilliantly connects algebra and geometry using coordinates on a graph. Third, don't worry, proofs aren't gone. It still hammers home the importance of building a careful, logical argument. And finally, it's constantly pushing students to take these ideas and apply them to real-world situations. But how does a big, fancy idea from a national document actually end up in a real classroom? Well, it's actually a pretty straight line. It flows from a national framework like the Common Core you see on the left, right down to the specific curriculum of a school district like Fort Bend ISD over on the right.
And this is where the rubber really meets the road. We're going to take a quick tour through a typical year in a geometry class to see how those huge philosophical ideas actually get broken down into day-to-day lessons.
So get this, the year doesn't even kick off with shapes and formulas. Nope, it starts with learning how to think. The very first unit is all about building the tools for logical reasoning, and that becomes the bedrock for everything else that comes later. And check this out. One of the very first skills a student has to master isn't just proving things true, it's proving them false. Right from day one, the goal is critical thinking. If someone makes a claim, can you find that one single example that totally breaks their argument? That is an incredibly powerful skill.
All right, let's jump forward a bit to Unit 4. And hey, look, it's our old friends, the triangles. But notice the name here. It's not just triangles, it's proofs of triangle congruence. The whole focus is on the how and the why.
And there it is again, that big idea. To prove two triangles are the same, students have to circle back to that core concept of rigid motions. Can you slide it, rotate it, or flip it to land exactly on the other one? It turns the proof from a boring checklist into a dynamic, active process. Okay, let's look at just one more example to see how things progress. By the time we get to Unit 7, we're talking about circles, but again, the theme is the same. It's all about discovering relationships and then being able to prove them logically. This is just a perfect, concrete example of what's expected. A student has to take a bunch of different ideas, tangent lines, a radius, a right angle, and weave them together to build a logical proof. It's all about connecting the dots. So we've seen what students are learning, but the how they learn it is just as revolutionary. The way teachers actually teach this stuff has gone through a massive overhaul to support these new goals. Look, the whole point here is to get way beyond what we used to call plug-and-chug math, where you just memorize a formula and jam the numbers in. The real goal is for students to genuinely get why the formula works, so they can use that idea in situations they've never seen before. And this is the main tool in the toolbox for building that kind of deep understanding. It's called the Concrete Representational Abstract Model, or CRA for short. And it's a super intentional pathway to lead a student from hands-on stuff all the way to symbolic math.
Okay, let's break this down real quick. It all starts with concrete. Students are physically touching things, moving blocks around, getting a real feel for an idea. Then they move to representational, where they learn to translate that physical experience into drawings and diagrams. And only then, after they've got that solid foundation, do they move to the abstract, the X's and Y's and formulas. This makes sure that those symbols are actually attached to real meaning.
So we've looked at the big ideas, the classroom, the teaching methods. Now let's just zoom all the way out one last time and ask, what is the end game here? What's the ultimate point of all this? Because, at the end of the day, it's not really about whether you remember some random theorem about a pentagon 10 years from now. It's about the mental muscles that you build getting there. The real objective is to develop a very specific kind of thinking, precise, logical, and creative. And this quote right here, this is the whole game. This is the absolute core of it all. Can you build a solid argument that's based on evidence? And maybe even more importantly, can you listen to somebody else's argument and poke holes in it, find its strengths and weaknesses? That skill is priceless, whether you're in a science lab, a courtroom, or a board meeting.
So, if you walk away with anything from this, let it be this. Modern geometry is about motion and relationships, not just boring static shapes. The real focus is on training your brain for reasoning and problem solving. And it's all about building skills for your actual life, not just for cramming for the next test. Ultimately, this isn't just a geometry class anymore. It's a logic class, it's a problem-solving class, it's a critical thinking class, it's just cleverly disguised with triangles and circles. It's about building a mind that's ready to analyze, to argue, and to create the world around us.
Which really just leaves us with one final thought to chew on. If these are the fundamental rules that govern all the shapes and spaces around us, from our phones to our skyscrapers, what does it really mean to understand them? How do the rules of geometry end up shaping the very world we decide to build?
We're just swimming in data every single day, right? It's on your phone, it's in the news, it's all over your job. It feels like this constant flood of information. So the big question is, how do you make sense of it all without getting totally swept away? How do we learn to actually read the stories that all this data is trying to tell us? Well, that's exactly what we're here to figure out.
I mean, you see charts like this all the time, showing us the price of gas has been on a total roller coaster for decades. Or maybe you see something telling you the price of a movie ticket just keeps going up and up and up. It really feels like we're constantly being hit with numbers and graphs telling us something. But here's the catch, and it's a big one. These visuals, these charts and graphs, they can be used to show you the facts, plain and simple. Or they can be used to mislead you, to actually distort the truth. And in this explainer, we're going to give you the tools to spot the difference. Okay, first things first. We need the right equipment for the job. So we're going to build a visual toolkit that'll help us understand the basic language data speaks. Our very first tool is the bar graph. I want you to think of it like a lineup. It's perfect for comparing different groups side by side to see, which one's taller, which one's shorter, who's the winner. And here is a fantastic, if slightly weird, example. This chart compares a few record-setting collections. You can see it instantly, right? The biggest collection is, wait for it, 3,300 airplane sickness bags. It's a bit crazy, for sure, but it's a super memorable way to see a bar chart doing its job perfectly. So the bottom line is really simple. If you ever need to compare different things, different products, different groups of people, a bar chart is going to be your best friend. All right, let's grab our next tool. This is the line graph. So if a bar graph is a lineup, then a line graph, well, that's a journey. It connects the dots and shows you how something has changed over time. Just look at the story of cell phone adoption in the US. This isn't just a list of numbers for each year, it's a dramatic story of explosive growth. You can literally see the trend, that incredible takeoff right there in the steep curve of the line. And that's all there is to it. Whenever you want to see a story unfold over minutes, days, or even decades, a line graph is the tool for the job. It's all about tracking those trends. Our final tool is the scatter plot.
Now, this one's for all the detectives out there. A scatter plot basically just throws a bunch of dots on a graph to help you see if two totally different things might actually be related to each other. So, take a look at the weights of giant pumpkins over a handful of years. Each one of those dots is a prize-winning pumpkin. Do you see a pattern? The dots kind of seem to be moving up and to the right, don't they? That suggests there's a relationship here. As the years went on, the winning pumpkins got heavier. And that really gets to its main purpose. Whenever you find yourself asking, I wonder if these two things are connected, a scatter plot is exactly where you should start your investigation. Okay, so now we've got the tools, but a toolkit is only really useful if you've got a good method for using it. So it's time to stop just looking at graphs and start thinking like a statistician. See, according to the Gase report, which is a major framework for teaching this stuff, statistics is way more than just crunching numbers. It's really a problem-solving process that always, and I mean always, depends on context to find the real meaning. And that whole process boils down to 4 key steps. First, you have to ask a clear question. Then, you go out and collect the right data. Third, you analyze that data using the tools we just talked about. And finally, and this is the most important part, you interpret what it all means in the real world. Question, collect, analyze, interpret. That's the mantra. So, now that we're armed with our toolkit and our 4-step method, we're ready for the final boss, spotting the traps. Let's take a look at how data can be presented in some really devious, misleading ways. All right, have a look at this bar chart comparing ice cream prices. Now, at a quick glance, it looks like Dag & Hawes costs twice as much as Ted and Jimmy's. I mean, the bar is double the height. But look closer. Look at that vertical axis, the y-axis. It doesn't start at 0. It starts at $2. And that is a classic trick. By messing with the scale, the graph creates this visual impression of a massive difference, when in reality, it's just 50 cents. It's a total distortion of the truth, and it's designed to fool your eye. So, rule number 1, always check the axes. Okay, here's the next big trap. Let's say you make a scatter plot and you find a really clear pattern, a clear relationship between two things. Does that automatically mean you found the cause? For example, this scatter plot seems to show that as the number of fast food meals people eat goes up, their body weight also tends to go up. It looks like a pretty clear positive relationship, right? But then, what about this one? This one plots fast food meals against test scores. The dots are just all over the place. There's no clear pattern here at all, no relationship. Just because two things might seem connected doesn't mean they actually are. And this brings us to what might be the single most important rule in all of statistics. Correlation does not equal causation. A scatter plot can show you that two things are related. That's correlation. But it can never, ever prove that one thing causes the other. Proving that is a much, much tougher case to make. So, we have covered a ton of ground here. The tools, the method, and the traps to avoid. And what you've gained is more than just a little bit of knowledge. It's kind of like a new superpower for navigating the modern world. Here's your checklist. First, always ask yourself, what story is this data trying to tell me? Second, inspect those axes like you're a detective on a case. Third, let's say it together, correlation is not causation. And finally, always question the context. Where did these numbers come from, and why were they even collected in the first place? And why does all this matter so much? Well, because sometimes the stakes are incredibly high. As the GSA report reminds us, the Space Shuttle Challenger disaster was, at its heart, partly a failure to properly analyze and present data. Understanding this stuff isn't just some academic exercise. It can have literal life-or-death consequences. So, from here on out, you're not just a passive observer anymore. You are now a critical thinker, an interpreter of data. The next time a chart or a graph flashes in front of you, you'll know what to do. The only question left is, what's the first thing you're going to look at?
Hey everyone, and welcome. Today, we're going to take a deep dive into the world of high school geometry. You know, it's a subject that can feel super abstract, kind of rigid, and, let's be honest, a little intimidating for a lot of us. But what if I told you it's undergoing a massive transformation? Let's explore the journey of geometry, from how it's always been taught to where it's headed now. Ah, yes, the question. The one that has bounced off the walls of math classrooms for, 100 years? It's the ultimate challenge from every student, and today we're actually going to answer it.
we're going to look at why we learn all this stuff and how teachers are making those lessons feel more real than ever.
Okay, so first things first. To really get where math education is going, we have to understand where it's been. And for over a century, the game plan has been surprisingly consistent. It's all been built on this bedrock of logic, proofs, and theorems.
For most of us, this probably looks pretty familiar. This exact sequence, Algebra 1, Geometry, Algebra 2, and then onwards to Calculus, this has been the standard college prep track for generations. It's a very structured, step-by-step progression, and it was designed with one big goal in mind: getting students ready for those high-level, calculus-based STEM fields at university.
And what's really interesting here is the flow, right? You start with the absolute basics: a point, a line, a plane. But then, almost immediately, you jump into reasoning and proof. So before you even get to the really complex shapes, you first have to learn how to build a logical argument. The shapes themselves are almost just the vehicle for learning how to prove things about them.
And this, right here, gets to the very heart of that traditional approach. See, the blueprint for geometry isn't just about making you memorize the Pythagorean theorem. According to educational standards, like these ones from Ohio, a huge goal is just teaching you how to think. It's about building a solid argument piece by piece, and then being able to look at someone else's argument and spot the flaws. Now that is a skill you can use absolutely anywhere.
But teaching logical thinking is one thing. Answering that classic question, when am I going to use this? Well, that means you have to make these abstract ideas feel real and tangible. And that whole process, it starts way earlier than you might think.
And this is just such a brilliant way to make learning fun. I mean, in elementary school, geometry is a physical thing. You're literally using your arms to make an obtuse angle. You're going on a scavenger hunt to find parallel lines on the monkey bars. You're building entire cities. The goal here is just to connect all these new kind of strange words, like lines, rays, and angles, to the world kids already see and play every single day.
Okay, so that's all great for a fourth grader, but high schoolers, they need a different kind of connection. The stakes are higher, the concepts are way more complex, so how do you bridge that gap and keep them from just zoning out?
Well, the answer for a lot of educators is something called project-based learning, or PBL for short. So instead of just solving a problem on a worksheet, students get to use geometric principles to tackle a real-world design challenge. And a perfect example of this? Building a bridge.
A project like the Toothpick Bridge Challenge basically turns students into engineers. They're not just handed a formula. They have to go research why one truss design might be stronger than another. They create these super detailed blueprints where every single angle matters. Then they build it, and the final exam is seeing how much weight their bridge can actually hold before it shatters. Every single step is a direct application of geometry.
And the impact is it's huge. As high school math teacher Nicole Bruce points out, when students are deep into a project like this, class just flies by. They're not watching the clock, they're solving a puzzle. And their confidence just soars, because they are seeing their knowledge create a real, physical thing that actually works.
Now, project-based learning is a fantastic tool, no question. But some educators are thinking even bigger. They're actually questioning the entire structure of that century-old math pathway. And they're asking, is one single road really the best way for every single student to get where they're going?
So on one side, you've got that traditional path. It's a single track, mostly designed to get students ready for STEM careers. Think engineering, medicine, that kind of thing. But what about everybody else? Well, on the other side, we're seeing the rise of these alternative pathways. The whole idea is to offer different math tracks that are just as challenging, but a whole lot more relevant to a way wider range of careers.
So what do these actually look like? Well, a future nurse might get way more out of a deep dive into statistics and probability than they would from advanced calculus. A future journalist could actually use data science to analyze trends and tell incredible stories. The key idea here is that the math is tailored to your destination, giving students the specific skills they will actually use in their jobs.
So when you put it all together, you've got the foundational logic, the awesome hands-on projects, and these new, super flexible pathways, a completely new picture of math education starts to come into focus.
And at the very heart of this whole shift is a really powerful idea, and it's captured perfectly by teacher Robin Allison. The goal is to move away from this myth of the math person. It's this belief that math isn't some talent you're born with, but it's a skill that literally anyone can develop, as long as they can see its value and its relevance in their own life.
So, ultimately, here's the bottom line. This evolution in math class, it isn't about making it easier, it's about making it more meaningful.
The big goal is to create a system that keeps standards high, but offers what people are calling relevant rigor, a really challenging math education that's directly useful for each student's future, whatever that future might be.
And that leaves us with one final thought. For centuries, math has been about finding that one single correct solution. But as we've seen, the future of teaching math might be less about that single destination and more about providing a map with many different routes, empowering every student to navigate their own unique journey.
All right, let's talk about a concept in math that, well, it trips up almost everyone. It seems so simple on the surface, but it actually reveals this huge mental leap that a lot of us just don't quite make. And to show you exactly what I mean, I'm going to give you a classic puzzle. As I read it out, just let an answer pop into your head. Don't overthink it. You ready?
Okay, so here's the setup. We've got Mr. Short. He's 4 matchsticks tall, which, for whatever reason, is the same as 6 paper clips. Now, his buddy, Mr. Tall, is 6 matchsticks tall. So the big question is, how many paper clips tall is Mr. Tall? Got an answer? Lock it in.
Now, here's what's so fascinating about this little puzzle. It's not just a puzzle. It's more like a diagnostic test that uncovers this hidden hurdle in the way we think about numbers. So, did you say 8? If you did, hey, you're in very good company. That is by far the most common answer people give. But it's not the right one. The correct answer is actually 9. And that's where things get interesting. Why? What is going on here? And believe me, this isn't just some cute brain teaser. Researchers have found that the specific thinking that leads to that wrong answer is one of the single biggest obstacles for math students all around the world. It's a truly universal stumbling block. To really get to the bottom of this, we need to understand 2 totally different ways of approaching the problem. There's additive thinking, and then there's multiplicative thinking. This difference, well, it's everything. So here's the breakdown. Additive thinking just asks, how much more? It's all about adding or subtracting a fixed amount. Multiplicative thinking, on the other hand, asks, how many times bigger? It's all about scaling, about ratios. So let's apply that. The mistake, that answer of 8, comes straight from additive thinking. The logic goes like this. Well, Mr. Tall is 2 matchsticks taller than Mr. Short, right? 6 minus 4 is 2. So I should just add 2 paper clips to Mr. Short's height. 6 plus 2 equals 8. It feels so simple and logical, but it's wrong, because the relationship here isn't about adding, it's about proportion. And look, this isn't just my take on it. Research nails this down perfectly. As one study puts it, the biggest mistake learners make is using additive reasoning when they really need multiplicative reasoning. The right way is to figure out the ratio. 4 matchsticks equals 6 paper clips, which means every matchstick is worth 1.5 paper clips. So you take Mr. Tall's 6 matchsticks, multiply by 1.5, and boom, 9 paper clips.
Okay, but the great news is once you can see the problem so clearly, you can start to fix it. So how on earth do teachers get students to make that critical jump from just adding things to really thinking in ratios?
Well, the secret is to make these abstract ideas, like ratios, into something real, something you can actually see and touch. They use these wonderful tools called manipulatives, which are basically just physical objects that let students play with the math. And there's a whole toolbox of these things. We're talking about Cuisenaire rods, Unifix cubes, pattern blocks, even simple stuff like colored beads or tiles. They all do the same job. They turn an abstract concept into something you can literally get your hands on. Let's just take a quick peek at a couple of these in action. First up, these little things called ununifix cubes. So, a teacher can click together a little train of, say, 2 blue cubes and 3 red cubes. Right away, a student can see the relationship. For every 2 blue, there are 3 red. Then they can build that pattern out, make it 4 blue and 6 red, and they physically see how the ratio, that 2 to 3 relationship, stays exactly the same. Or what about pattern blocks? These are just amazing for getting a feel for fractions and how parts relate to a whole. A kid can just play around and discover on their own that exactly 6 of the little green triangles fit perfectly inside the big yellow hexagon. Nobody has to tell them that the triangle is 1/6 of the hexagon. They feel it, they experience it, and that kind of hands-on discovery builds a way deeper understanding than any worksheet ever could. Now, moving beyond the classroom, researchers have come up with some seriously clever ways to figure out not just what kids are getting wrong, but to understand the why behind the mistake. They've developed this cool thing called a 2-tier test. So the first part is just a normal question, like our Mr. Tall puzzle. But the second part is the clever bit. It asks the student to choose the reason why they picked their answer. This lets researchers see if a right answer was just a lucky guess or if a wrong answer came from that classic additive thinking mistake.
I know, this diagram looks absolutely wild. Don't even try to read the boxes. The big idea is actually pretty simple. Think of these tests as a kind of brain scan for a student's mathematical thinking. It lets researchers map out the hidden pathways of their logic and pinpoint exactly where things are going off track. It's diagnosis on a whole other level.
So, we've seen the problem, we've seen the cause, and we've seen some of the solutions. But let's just pull back for a second and ask the really big question. Why does any of this matter so much?
Well, because it's not just another topic in a textbook. As the experts tell us, proportional reasoning is the absolute cornerstone of algebra and pretty much all higher-level math. If that one stone is wobbly, the entire building is at risk of collapsing.
And this goes way beyond just passing a math test. It's about functioning in the real world. You use proportional reasoning every time you try to figure out the best deal at the grocery store, or scale up a recipe for a dinner party, or even just read a map or a blueprint. From science to art, from cooking to finance, this kind of thinking is everywhere.
And that leaves us with one final big question to think about. If this skill really is the foundation for so much of higher education and just everyday adult life, we have to ask ourselves, are we doing enough to make sure every single student has the right tools, both the physical ones and the mental ones, to build that cornerstone strong and secure?